So I had a little introduction here, but because of the time problems, I'll probably skip it. So I was hoping to talk a little bit about software engineering. What does it mean to be a software engineer? What kind of rigors you have to have in your day-to-day discipline, and then how that applies to functional programming, trying to convince you guys that functional programming is actually the way to go to be actually a software engineer. But as I said, I have to skip that introduction. And we will directly go to the main theme of this presentation, which is recursion. Recursion, unfortunately, is still a problem in functional programming paradigm. I mean, if you're working with strongly dependent languages that are total, that you have those guarantees within the language that if you have a function and that function returns a type, it will always return that value and nothing ever will happen ever again. But we don't really deal with those kind of languages. Even if you do Haskell for a living, if you do Scala, things might break. Like if you have a function that gives you a string, that function can still crash, can still throw exceptions, weird things can happen. So we don't really have this guaranteeing when we work with those with recursion, and that's actually a pain and a problem. And let me show you why. So we'll be talking about recursion schemes, which were described in this paper, and you may recognize the names like lenses, bananas, envelopes, and barbed wires, because those are actually the names of the rooms within this conference. This talk is sort of based on this paper a little bit, I guess. That paper describes recursion schemes, which are simple and composable combinators. For some of you that might not really need anything, but we'll see in a moment what that really is. And also a process and a way of how to traverse and deal with recursive structures. So now the question would be, what are recursive structures? Recursive structures are any basically structure that is defined inductively, meaning like, for example, list. So list is a nil, and this is also a const, and const is a value and a list. So now you have this induction step in the way you define your structure, or things like, for example, binary tree. But recursive structures can be more closer to your real world, to the business value, to the business object that you have in your system. So it can be a file system, it can be a 3D scene, it can be your database, or it can be your business report, whatever that is basically inductively defined. Now, for this talk, I've created this little example of expressions, because if you really think about expressions, they are sort of this recursive structure, right? You define, like, you might have this equation here, like you sum two elements together, two expressions, where the first element is 10 squared, and the other one is multiplication between two values. And if I, for example, would like to square this whole thing one more time, I have to square this thing one more time, I would just compose that thing in one more square. So we'll be using this example throughout the rest of the presentation, and you might be thinking, oh, this is sad. Like, this is a very simple example. And I was thinking firstly about creating something more closer to the business, but then I reckon maybe, just maybe, you guys would focus more on the example per se, rather than the things I try to describe. That's why the example is simple, because the stuff I would like to talk about might be a little bit complex. So you can think about this expression also as this sort of tree, right? We start with our root, which is square, then there's sum, and the elements of the sum is one more time square and multiplication. At the very bottom, at the level of the leaves, are your values, like 10 or 20 and a half, and so on. Now, this is how would we describe this structure in Haskell, and this is just everything we just said a moment ago about what expression is. So expression might be a value, or it might be sum, where sum is just expression and expression, and so multiplication and so on. In Scala, it looks a little bit more verbose, but that's why we use sort of this color highlighting, and when you focus really, really hard, you will see the important stuff right here. Okay, so now how could we write a function that would evaluate expression? This is really not a hard thing to do, right? Well, if there's an integer value or if there's a double value, we just return that value. If we have something that uses that recursiveness within our structure, like for example, we like to evaluate sum, well, then we have to first evaluate the left-hand side, and we have to evaluate the right-hand side, and having those two values, we can sum them together, right? Isn't really rocket science at this point. If I had a function that the idea behind this function would be to print my expression to the console or whatever, the function would look something like that. And it's not, like, you might see that actually there's a pattern here, right? We always tend to try to separate our concerns, and for those two functions, we have two separate concerns. One is actually responsible for traversing the structure, because whenever we have something like sum and multiply, we have to go deeper and deeper until we reach the leaves of our structure. And the other bit is actually summing or printing the representation of the given expression. Now, you might say that, okay, that's a problem, but not really that hard problem. Maybe I could work around it. But there are other issues that we might have here. So for example, this is a function optimize. An idea behind this function is, if I have a multiplication and I multiply expression 1, expression 2, and those are exactly the same, I would rather change the structure to be just square of one of those expressions. And it makes sense, right? From the performance perspective, it actually makes sense, because if I were then to evaluate this expression, it's just easier for me to evaluate xp1 once and then square it, rather than evaluate this expression once and the second time and then multiply them together, right? So, but the problem is with this function, it will unfortunately not compile, not yet. We still need to deal with all other cases from our structure. And all those other cases aren't really doing anything. They are just traversing the structure that we define. We have to go deep into until we reach our leaves to get the values back and go back and do whatever optimization that we are doing. So this example is simple. Imagine something which is a little bit more complex. Now we have your huge function where only 2 lines are important. But that's not really the issue here yet. Think about this little error that I made here. Instead of, in the multiply case, instead of calling optimize for expression 1, I forgot about it. Will compiler complain? Not really. Compiler will be completely happy about the way I implemented this function. He'll be like, you're good, go for it. Most probably I will write tests for it, but the test that I will write will probably deal with the optimization part. And if by any chance my test example doesn't have multiplication, instead has a sum or division, then I'm screwed. Because that error will eventually pop out in production, but not in my tests on the compilation time. What happens if I will call optimize for leaves? Like, for integer value and decimal value, those are the values that should actually return a value back. But I can call optimize on them as well. And this program will run infinitely. This will never, ever execute. They will never give me a value back. But compiler will be happy. If you would like to visualize how this program works, it's not really that hard. We started with some value. We go first to the left-hand side. Left-hand side is a sum, so we also have to go to left-hand side, so we get a value back, get the right-hand side. Then we have to evaluate the right-hand side of the multiplication, and so on and so forth. And sort of like you see that we start from the root of our structure. We go to our leaves, we pick up values, and go back. And while we're going up, we do the business logic, whatever the business logic is. And the same thing would apply for this function make string. Would be exactly the same functionality. Traverse, do your business logic, and go back. Now, the question is, would it be nice if I have just some machinery that would do that thing for me? Like this evaluate function, as I said, has 2 separate concerns. Evaluating my expression and traversing a function. Wouldn't it be just nice if I had something like that? If I just had a function that can only deal like, what does it mean to multiply 2 doubles together? What does it mean to sum 2 doubles together? And there would be some separate machinery that would go through my structure and only call this function for me. All the errors that can happen, all the recursion would still be here. We'll still be dealing with recursion, but the recursion would be completely implicit instead of explicit. It's like with goto statements. Do we have goto statements in Scala? We sort of have them. They are in the bytecode, right? We deal with whatever for loops and while loops because that's a higher level abstraction, but implicitly, go statements are still there within our bytecode. And the same thing applies here. I would like to have a machinery that would do the recursion for me, while I, as developer, can only focus on stuff that's really, really important. So in order to have this function, I would have to change the signature of my expression a little bit. So instead of having this, I would have to, because that evaluate will be having expression of doubles because I only want to deal with doubles. Make string will have to deal with expression of strings because I only want to deal with strings at this point. So I would have to change this example to something a little bit more bizarre. I would have to leverage the parametricity I can have within our language. So now expression in this new form, if we take, for example, multiplication, it no longer has two expressions, it has two a's, whatever those a's are. Those might be strings, those might be doubles, whatever you will choose when you create examples like that. So we are almost there. You can almost create this function that we want and probably the machinery that we need. But we have a problem. We created expression, the first one, to basically represent expressions, right? I would like to represent 10 plus 2 and multiply it with some other 20, right? How can now I create this example using this new signature here, using this new representation? Is it still doable? How many of you guys think it is? It sort of is, but it really isn't. And let me show you how that is. So let's start with this simple example. On the left-hand side, you see the old way how to create expressions. So we had two integers, and we summed them together. Now, we have this parametricity here, and we need to fill those question marks. If we really, really look at the leaves of our structure, it doesn't really matter what I put A for int value and decimal value. I could put here string, user, integer. It doesn't really matter because A is not really used on the level of our leaves, right? So I could put unit, and this would be just fine, right? It could be expression of unit because we don't really use A whenever we deal with integer values or decimal values. Okay, so that's good. But what about sum? Well, we see that this thing is expression of unit. That thing is also expression of unit. And if we look at the sum definition, sum is saying, I will have two a's. What is a in our sum at this point? It's expression of unit, right? So I can just put here expression of unit. Then the final our type that we're having is expression of unit. And you might be like, huh. And I understand, but it's getting worse. So let's have a little bit more complex example with two levels of those things. I'll just go a little bit faster. So one more time, we put a unit to our leaves, then this becomes expression of unit, then this also is expression of unit. So divide is expression of unit, so our final type is expression of unit. If you think this is stupid, then think about this example. What if, if you're used to being Java developer, you sort of deal with boilerplate, I get it, but think about this example. What happens if let's say I have a function that parses some string and should give me an expression back. In that previous representation, I would just give you a function that returns an expression. Now, what about a new representation? If I don't know how many levels of my final structure has, how many expressions of unit I should put? Infinite? Obviously, that will not compile, but I cannot really do anything like that, and that's a problem. And the question is the problem solvable? Unfortunately, it is. So introducing fixed point data types. There are many fixed point data types. We will focus only on a single one, which is the easiest one, which is called fix. Now, for people who will see fix on the first time in their life, this will be sort of troubling experience. That's why I'm bringing you a cat, so your brain can relax. You can chill. Like professional speakers, They will tell you a joke at this point during the presentation, so you can relax. Like Venkat Subramanian will tell you jokes about his wife. This thing is being recorded. I will never say a joke about my wife while things are being recorded. But you should now relax. Okay, you good? You good? Fix. All right, so fix looks like this. It isn't really that scary if you think about it. So let's try to decompose it, all right? So fix. Fix is, first of all, parameterized by some type constructor, okay? So far, so good, by some f. But where f just is as a type constructor, meaning it creates a type. It could be like an option or something like that, or our expression, right? Now, fix is a wrapper class. It is a class that wraps something. It has a single constructor that will take something as some element when we will instantiate an instance of fix. And what does it take? Well, it takes that our f, but at any f, only f that is parameterized by fix of f. Okay, this is bizarre. So let's try to work with an example. Remember how we had this expression of unit. Let's try to put fix into those expressions. So let's start with leaves. I will wrap my expression within fix, okay? So now the question, what should be instead of those units there? If you look closely, if you look really, really closely, and we don't have time for it, you will get this. Now, this might look weird for you, so let me try to decompose that for you. So we wrapped our expression within fix. That's this part. So we created a new instance of fix, and as I said, the fix will have a constructor that will take one thing. And what it's taking? It's taking our f, where our f here is an expression. Now, it cannot be any f. It can only be f that is parameterized by fix of f. So we are sort of, in order for this thing to compile, it needs to be parameterized by fix of expression. Now, if that looks bizarre, like, sorry, we don't have time for it, but just believe me, it compiles. So now, having this, we can go one level up. So now, we closed over fix our leaves. Now we have to close over fix our sum. So we will do exactly same thing. And if we close fix over sum, we get this fix of sum. And our final type is fix of expression as well. The same thing will apply to even deeper example like this one. Let me just skip it. So I basically go through from the leaves, I'm going up, and just close every element within fix. That's all I'm doing. So fix, 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 and fix. Now, compiler, Scala has a little bit of type inference. Fortunately, here it will work. So we could remove a little bit of that boilerplate. We can remove this. And our final example looks exactly like that. There's still some boilerplate, like you still see this little fix here, but it sort of reminds us of that original structure that we had before, right? And we can create those how many arbitrary fixes that we want, even for our parsing function that we had in a previous example, because in the type definition, we kill this recursion. We just say fix of expression, and that's it. Now I have a question for the audience. If I have a fix of an expression, how can I get expression back? Is there a method? Is there a way to do it? Unfix. I just call unfix, and that gives me that f. That gives me my expression back. That's all I need. So this is brilliant, right? Now we have ability to write this function the way we wanted to write it. So instead of evaluating stuff, but also traversing the structure, we can just only focus on evaluating things. And we also have machinery that allows us to create those expression examples using that fixed point data type. So now, what about that machinery? So that machinery, depending on the language, is implemented in different libraries. The one that is available in Scala was created by my colleagues, and it's called Matryoshka. And so in order to use it, we will have to provide a few things. But all we really need at this point is that machinery that will traverse our structure. Once we have it, we're good. So let's see how that goes. The machinery that we need is called catamorphism. Catamorphism was described in this paper. And you will see different morphisms appearing in this paper. But those are just really weird and complicated names for very easy and natural things. Like, for example, catamorphism is basically a fold, nothing else. Well, let's see how that goes. Basically, we need a mechanism, remember, that will traverse our structure, reach our leaves, grab the values from the leaves, and then go back, and while traversing back to the root of our structure, call our business function method, all right? So we need two things. We need a functor in order for that machinery to work. Why functor? Because, well, if we want to have some general machinery, it needs to have at least some information about a structure in order to traverse it. So that's one thing that we need. And it will also need that our function, which we a moment ago defined. So I will sort of guess, like how many of you guys are not familiar with what a functor is? Okay, only a few. So a very quick 101 to type classes. And I was just going to skip like most of those slides. But the idea here behind this is that if your type is a set of values within your type system, then think of a type class as a set for types. But it's not any set of types. It's like if you are a type and you would like to join my club of being a type class, then there's this function that you have to define. And you will define the implementation for this function, and you will be like, can I join your club right now? And you'll be like, no, wait a minute, there are some laws that your implementation have to go through, and if those laws applies, then you're good. In practical terms, it means that if I have a type class, let's say like a functor for some f, if there's an instance for that functor f, it has to implement that map method. So here map is basically something simple. So think of in terms of an option, right? Or an expression. If I have an expression of double and I would like to have an expression of string, I can define a map function that will go from double to string. And with that function, I can create an expression of string from an expression of double. And I will skip through most of those slides because most of you guys have a decent understanding of what a functor is, so hopefully that sort of makes sense. If you need like super 101 TLDR, it's basically if you have an instance for a functor for your structure, magically you get a map method that will allow you to go from one representation to the other. So we need to implement functor for expression. That's the only thing that we have to do. And it's sort of straightforward. There's no really magic behind it. It's just calling f on every element of your A. And that's basically it. Now, so we have this. We have functor. We're good. Now, we only need to implement our function. Now, our function actually has a name. It's called f-algebra. And you might be like, oh, God, another weird name. It's not really, there's no magic behind it. So this is the definition of that f-algebra. So f-algebra fa is just a function that will go from fa to a. So algebra expression integer is just a function that goes from expression of integer to integer, okay? A type algebra of expression and string is a function that goes from expression of string to a string. So we could define our evaluate, as you've seen before, exactly like that, where we only focus on the stat that's really, really important. It's just the type changed a little bit, and we said it's in the algebra. But underneath, it's basically, it's an alias for a function, okay? So having that function, we could, okay, sorry, and this is a definition for make string, where one more time we're saying, how can you go from expression of string to string? Because that's only the business part of this function that we're interested in, not the how to go through our structure. So now let's have an example. So with an evaluate, we can take one of our examples we created before. So this is that expression that divides few numbers, and there's sum and decimal value in between. And if we would like to run this evaluate on this expression, using that library Matryoshka, where Matryoshka provides all those recursion schemes, all that machinery for you, if you have that library in your project and proper imports are important, you will get this magic method, kata, for catamorphism, and it will run your evaluate function for your structure and give you the value back. It will essentially run your function evaluate for each of the elements of your expression, and we'll just traverse through your expression to the leaves, take the values back, go up, call your function, and finally merge the final result. Same thing goes for make string. Exactly same magic will happen. It's one more time calling cata. Now remember that optimize method, right, that we had before, and the problems of having that the only first two lines actually matter. Everything else is just boilerplate and not just dealing with compiling being happy. When we try to implement it in terms of algebra, we get this little definition, where we're saying what's important and everything else just, move forward, nothing else. And optimize will work as well. So here we have a multiplication of two same exactly expressions, and if we call catamorphism with that optimize method on that example, we will get the optimized version of it. Now, there's always just catamorphism, and there's tremendous zoo of morphisms within the right now recursion scheme. Some which were described in that original paper, some new are described in newer papers, and they are all really not that difficult once you actually understand what they're doing. We will only focus on two more, but really, really quickly. There's one called a monomorphism. An anamorphism is dual to catamorphism. So when I had a catamorphism had a structure and just folded to value, anamorphism is something else. I have a value. I have an integer, let's say, and it will explode the structure. It will create expression for me. For example, in this example, it will take an integer and it will just create expression where it's that multiplication, 2 multiplies by 2 multiplies by 2 multiplies by something, and that expression that will create will represent that initial value that we provided. So what we really need is something called coalgebra, and as I said, it's a dual to algebra, so obviously this will have a changed arrow, right? We will have a that goes to FFA. So we have some value like integer, and we would like to have expression of integer back. We have some string, we would like to have expression of string back, and so on and so forth. So now the implementation that I had in this example in the slide before would be really, really straightforward. I mean, I would just say, well, if my integer, that a in this general definition, is something that is divisible by 2, what I will give you is an expression which will represent multiplication, 2 and the other part, so n divided by 2. And it will go on and on until it will reach a point where n is not divided by 2, and then I will just return that integer value n for you, and that's it. So now if I run anamorphism, so ana, for my method for 12, it will create that expression where it's basically multiplication of 2 by 2 by 2 and by 7. And that's it. I think that's a wrong example. It shouldn't be really 12, but something else. But I think 28. But let's say it compiles. And that, so you see this just changing the arrow, and we have a new morphism. We have new recursion scheme. Now, hylomorphism, you will understand hylomorphism, let's say, in 5 minutes. Even faster, I think. So hylomorphism is nothing else as constructing and deconstructing a value. So it's just running anamorphism and after that running a catamorphism. So in other words, we start with a value, we run anamorphism on it. So let's say we started an integer and that gives us expression of integer back, and then we run catamorphism. That will, let's say, catamorphism, let's say, evaluate. So it will evaluate that integer, or maybe create a string representation of that integer. So first ana, then cata. And hylo is basically that one single arrow here. Now you might be thinking, okay, so what's the point? Like, why should I actually use hylo if I have those two and I could compose them together? And yes, those two can compose. Well, the thing is, if you run first anamorphism, try to visualize it. You start with a value, and the anamorphism recursion scheme will run this machinery. So it will just create a structure. At some point, it will have this stop argument within the algorithm. It will stop, and it will give you the structure back. So you have a single pass here. Now you will have catamorphism that will take that structure, which will go through that structure to leaves, and then go back and give you a final value back. So now you have two passes, right? It takes time. What hylo will do, it will run those two morphisms, those two recursion schemes simultaneously. So while Anna is creating the structure, at the same time, Kata will traverse the structure. Anna is done, and Kata will just go back with a value. It's just faster. And here you have an example where I just created some. So given those two previous, one was this divisor, which created that expression from a value, so 2 multiplied by 2 multiplied by 2 multiplied by something, and the other catamorphism, another one, algebra for catamorphism, just evaluates an expression. I can write like a property-based test. I could just, for example, test if those two work together properly. So for any arbitrary value, whatever value that you create, I could just, run anamorphism for that value, so that would create an expression, and then catamorphism to evaluate that expression, and that should give me the initial value back. So for any n, this should be always the same value. And instead of having that, I could just call it high-low. And as I said, it's only just run faster, but underneath semantically, it's exactly the same thing. Now, what else? Well, there are many places where you could actually use recursion schemes. And the best example that how much time do I have? Like 10 minutes? Cool. The best example that I normally talk about is, the place that I work for, it's Slam Data. One of the things that we do, the main thing that we do, is basically write a compiler. And when I mean we, I mean my colleagues, because I'm just too dumb to understand it. But the idea is that if you want to write a compiler, you have two ways to actually do it. So think about Scala compiler. Think about for comprehension. Like we all know for comprehension is basically a sugar for calls to flat map and map, right? And now try to think, how would you write a compiler for Scala code? Where there are basically two approaches that you could do. One would be something which they called monolith approach. And monolith is approach where you take an AST, you take the source code representation, and you all the little magic, and you just throw out assembly. You throw out bytecode that is ready to run. And this is implementation for a compiler that will be probably smooth and super fast, but super, super ugly. Because all of those places you have to, for flat map, you iterate this bytecode, but this is for comprehension, and I need to first do some magic to change that into flat map, and then give you a bytecode. It's just horrible. It's just horrible to maintain it, horrible to test it. So other approach, which actually Scala has, is called multipassing. So the idea here is that you take your original AST and you run it through the first phase. Let's say that first phase will desugar all your for comprehensions to a calls of flat map and map. So what you have is basically a first phase. Let's say we'll take all your comprehensions and give you a new AST back, but that new AST will get rid of all the for comprehensions within that definition. And then from that representation, let's say you immediately go, let's say, to bytecode, because that's obviously not how Scala compiler works. But you have those two separate phases. Now this is awesome from the maintenance point of view, right? Because what you can do is you can focus really on this one particular thing, which is desugaring your source code from flat map to, from for comprehension to calls from flat map and map. And then you can test it, you can reason about it, and you have a running thing. And then you can sort of focus on other stuff separately from each other. So from the maintainability point of view, from the testability point of view, this is brilliant. However, this is super slow, right? And now we have this dilemma, which one to choose, maintainability or the performance. And recursion schemes give you both of two worlds. Because what you could basically do, if you write like compiler like that, you could define those little steps in terms of catamorphism or anamorphism, so in terms of recursion schemes. So you still have this maintainability, this testability, right? Because all those little things, I can test what it means to go from AST to a new AST that desugar for comprehension, and I can have all those little steps defined as catamorphism or anamorphism. But my final compiler will just compose all those things together. So my final compiler will be composition of all those little recursion schemes. It will combine to one great thing. So I have, in terms of running this in production, I have a monolith. In terms of testing it and maintaining it, I have multipassing. And that's just brilliant. Now you might think, where actually I could use recursion schemes. Like basically, you could use recursion. You don't really have to do functional programming to use recursion schemes. Whenever you deal with recursion, especially recursive structures, recursion schemes are there for you. And in our code base, at least to the level I understand it, recursion, like explicit recursion, is right now considered a code smell. And we've run into bugs and errors only because we used explicit recursion. If you're keen on creating an open source project, I only know implementation about recursion schemes in Haskell, in PureScript, and Scala. If there are any other languages that you think could use a recursion scheme, there's like a space right now. And recursion schemes are becoming a very popular thing. So you want to be a popular, open source maintainer, there you go, create an open source project. I think that's all I have. Matryoshka is stored under this GitHub repository at SlamData. If you would like to see how actually, if you want to play around with whatever recursion schemes that you may think of. Quasar is the project that I'm working on, and we use recursion schemes extensively. So if you want to see the dragons and goblins and all the nightmares, is basically place to go. And it's open source, so you can also study the code base. Reference for my talk, the slides will be available. Probably I'll push them to Twitter. My name is Pawel Szulc. I have a Twitter account for you guys to complain, and I have an email. And a blog which is apparently down, but will be probably open on Monday one more time. Forgot to pay the invoice. All right, that's it. Thank you very much.